We are at our 8:30 slot, our third presentation for the education session. Up next is Tanya Hardon from the University of Colorado at Boulder. The title of her talk is DANDE, Operations and Implications. Welcome. I do apologize. We have a dual presentation. It's Tanya and Franklin Hinckley as well, both from the University of Colorado at Boulder. Welcome again.
Good morning, everybody. I'm Tanya Hardon. This is Franklin Hinckley, and we'll be speaking on DANDE Operations and Implications. DANDE was the winner of the University NanoSat 5th competition cycle and launched in September 29th of 2013. The focus of our presentation will be the lessons learned from a student team who has designed, tested, built, and operated a satellite. Oh goodness. Okay, so DANDE is this is very fickle. So DANDE is the drag and atmospheric neutral density explorer, and the purpose is to characterize drag in the upper atmosphere. Density fluctuates greatly at this altitude, so better characterization of the atmospheric makeup will help us better understand this environment. Okay. So on the screen is the basic drag force equation. The values shown in blue are coefficient of drag, cross-sectional area, and mass, which are all known prior to launch. This is the driver requirement behind DANDE's spherical shape, as coefficient of drag and cross-sectional area do not change based on a sphere's orientation. We then collect the values in green using our science instruments, specifically our accelerometers and our main science instrument, the wind and temperature spectrometer sensor. So with the collection of that data, we are able to solve for density and force of drag.
We're going to start advancing back here, so if you want to advance, just on the next slide.
Okay, I believe this is the slide that I want now. So this is our fully integrated DANDE satellite on our light band. The light band connects DANDE to the launch vehicle, and in order to ease that connection, we have a light band adapter bracket, as you can see over here on the right. We also have our main science instrument, our accelerometers, and our torque rods, this is the body y-axis, and that is our ideal orientation, so we can collect our science data, and DANDE is a spin stabilizing system. Next slide. So DANDE launched on September 29th, 2013, and for the first month we spent checking out the health and status of the system. Once we deemed DANDE was stable, we moved on to separation on October 30th, where we achieved a minimum mission success. Since ejecting our LEV is so important to be able to return DANDE to that spherical shape, that is what we deemed as minimum mission success. So then we spent the next 2 months checking out our attitude instruments. We lost contact on the 9th of January this year and had a brief recontact on February 7th of this year. Next slide. So activation. Our first phase was to check out the health of the system. We actually received beacons from DANDE hours after launch, but as the launch objects began to separate out, we had some trouble with communication, so we spent about a week determining which launch object was DANDE to reestablish that constant communication. After that, we finished our health and status checkout and moved on to separation, where we actually worked with Air Force, Maui Optical and Supercomputing Observatory to visually observe the separation, which was an incredible opportunity to receive visual confirmation of our mission success. DANDE does not have a GPS system, so everything is based on system time, which made it a little bit more difficult to target separation over a specific location. We made some modifications to our scheduler program, and the photo on the right shows 2 distinct objects, proving that not only did we separate, but our timing was correct. Next slide. So after we separated, we moved on to our ADCS instrument verification. Just to reiterate the importance of DANDE's orientation, we have the ideal attitude shown with the velocity vector aligned with the body y-axis. Our main science instruments, it takes our data out of that velocity vector, so we want to make sure that we're going correctly and we're aligned correctly. In our original concept of operations plan, we were not going to verify the magnetic readings that came out of our magnetometer, as we only had about a week to do the whole phase, and we thought the the verification on orbit would take too long. However, we were put in an orbit with a significantly longer mission lifetime, so we decided to do these verifications a little bit more in depth. So our problems with the magnetometer verification was that we didn't have an independent knowledge of Dandy's attitude. So without that independent knowledge, we couldn't verify the attitude solution that came out of our magnetometer readings. So we were forced to kind of fall back on the assumption that those readings were correct, like in the initial plan, and move on. Then we moved on to our torque rod verification, where we had trouble downlinking the data since the files were so large. As Dandy approached the loss of contact, our link was less and less stable, which made it even more difficult to downlink the data. And so we were forced to kind of push through that data, push through that processing, and continue on with our mission. And the team learned a valuable scope creep lesson that, stick with your concept of operations plan, stick with what you were intentionally going to do, and don't change on orbit. Next slide. So moving on to our operator training. Our team is exclusively students, most of which are undergraduate, and it poses a unique challenge because these students have never designed or built or especially operated a satellite, and we haven't really used a lot of the analysis tools or the model designing tools that are used in industry. But through this opportunity, through the DANDE program, we were able to complete complex analysis and thermal models and use industry-level tools, and we got an incredible amount of industry mentorship from testing facilities to reviews by industry partners, and just being able to ask questions and get in touch with the right people was incredibly useful for the DANDE team. Next slide. So to exemplify the experience that we gained, here is the full SolidWorks model of the DANDE sphere. Next. This is the model that we used in Thermal Desktop to do all of our thermal analysis. Next. Here is our schematic of our wind and temperature spectrometer controller board in Altium, completely student designed. Next. And the last is a spectrum analyzer capture of our beacon showing kind of some of our comp testing. Next. So while we were a very successful mission, we definitely have some suggestions for future operators, especially student teams. Every operator needs a very good understanding of the system. It's not expected that everybody's an expert. You can't have every operator be an expert, but we had issues with some of our things, especially ADCS commanding, where there was only a few operators that knew what command stacks needed to be built, what needed to be sent up to the satellite. So we had to base those commands on when those students were available, which, there's coursework and all sorts of other things, and it puts a lot of extra strain on students. So having a team where everybody knows enough so that, given any group of operators, they can perform those tasks needed for a particular task is very helpful. Our other big takeaway for training was to integrate the operators and the engineers early. The engineers definitely need the perspective of an operator so that when they finish that product, it's very easy for the operators to use. And the operators also need to understand that hardware and software component so that they can effectively operate the satellite, and if anomalies pop up, those students know how to handle it. And if you integrate those teams early, next, you will avoid this issue where engineers are like, I have a brand new person, it's going to take me so long to train them, I might as well do it myself. But if you take that time in the beginning, those operators will then be technically knowledgeable enough to help operate the satellite and to run things later on in the mission.
Next slide. But one of the tools that was particularly useful to the operators during operations was the ability to bring in data sets from a wide variety of sources and then be able to overlay that data in a format that was useful to the operators working through the mission. Here we can see the discrete black data points, which are EPS data for the voltage on the 12-volt line. We have illumination time per day from SDK, which is the purple line, and then proton flux data from the GHOST satellites, which is the blue line. That plots like these allow the operators to see a coincidence of the drops in voltage here and here with the period of total illumination to reduce efficiency on panel arrays and increase temperatures. Also to see the drop in voltage here with the torque rod testing, and then to see the loss of contact here coincident with the large increase in proton flux. That producing plots like this both bring the value to the mission to be able to bring in all of that data, to be able to see those correlations, then was also provided the operators the experience with figuring out what data they needed to proceed with the mission, how to present that data in a form that was useful to them, and then to outside help brought in for the mission, and then also how to then actually interpret this data. Unfortunately, the tools needed to produce plots such as this had needed to be developed on orbit, as the prior tools which were designed to process the data coming out of manual life testing were not particularly easy to use for processing large amounts of data from a wide variety of data blocks from the satellite, and would also give timestamps for the data in terms of the system clock, which for most of the mission then was seconds since launch. So trying to correlate an event that happened 2.7 million seconds after launch is really a very difficult unit to work with. Next slide. Another of the big tools was the beacon. The DANDE had a beacon interval of 15 seconds, which basically without a GPS is really the only way to verify where the satellite was, so that when you're dealing with that string of pearls issue after launch, then successful reception of the beacon is really the only way to verify both that your ground station is indeed tracking correctly, that you're pointing where the satellite is, and then to figure out which of the various canned objects is indeed your satellite. 24% of all of our data over the course of the mission was actually received in the form of the beacon, which really illustrates the utility of making sure that all the fields in the beacon really are data that's useful to the operators. That our beacon was originally written as a day-in-the-life debugging tool, so it had some fields, for instance, the help of the transmitter, where that is kind of implied by having actually successfully received that beacon. So a very good source of these beacons was the amateur radio community. 3/4 of all those beacons were submitted by amateur operators, including many more that were not fully framed when we received them, but most likely contained useful data. That amateur radio community provides much better temporal and spatial resolution than would otherwise be feasible with just a single ground station for a university project. The map here shows the locations of the operators who registered on our Beacon Portal website for submission of beacons. Note that the first and last contacts with DANDE were actually submitted by amateur operators, showing just how useful they were to the mission for getting that additional data to really help the operators work through what was going on. Next slide. Another issue that came up was how the satellite was active and absence of active operators. Really, the operator should be able to go missing for an extended period of time and find the satellite healthy when they return. And some of the issues that need to be addressed to make this possible are if there's any issues on the satellite that require active operator management to stay on top of. An example of this was on DANDE. The accumulation of files in the file system would also increase the load on the system processor, as you can see in the trend here on the plot. As DANDE had no ability to autonomously delete files, this trend would continue until the processor became inoperable. Another important issue for the stability is how the power usage is. Without operator commanding, certain mission tasks will certainly be power negative in the short term. The satellite needs to be able to identify if it is going into a power negative state on its own, and then be able to mitigate that to ensure that it doesn't, that it remains power positive or at least power neutral without operator involvement. Other issues, contingency planning, that any mission, no matter how well you've thought through your design or operations, there will be errors that will occur. And if the satellite is able to identify and respond in some manner to those errors to mitigate the effects, that'll make the mission, increase your mission duration, make everything run much more smoothly. That really your main tool we found was to have a really robust and thorough safety mode. You have the wide and diverse entry conditions to be able to handle many errors going into the mode. To try and have minimal functionality in that mode, particularly power issues, the file generation issue we mentioned. Make sure you're not making those errors worse, so that theoretically you should be able to remain in the mode indefinitely. Next slide. As the operators are actually conducting communications out to the ground station, it's important to have the ground station team and the satellite operators well integrated. That both operators have been trained on the proper uses of the ground station, that this training really got not to be a very good substitute for actual hands-on experience. And then during operations, as there was always the pressure to get any debugging repairs taken care of before the next pass, not losing any of that precious pass time, then the ground station team would handle the debugging so the operators did not gain that experience. And then suggestions to mitigate those issues we saw were to have the operations team assist in the pre-launch verifications of the ground station. We have a lot more time to work through, take the time to let the operators work through those issues and then learn the skills they need to be able to then debug later. And then to try and avoid that usual engineering tendency to have the most experienced engineer present or take charge, figure out the issues themselves, than to really stand back, let the newer people work through it so that then they have the experience they need later, so that then you don't need those senior engineers continuously debugging everything. Next slide. Reiterate that this was an entirely student team that gained the professional level project experience with those industry standard tools. I think it's fair to say that the students who are working on this project are where they are today in no small part due to the work they did on the DANDE satellite. So I'd like to end with that even though most of this presentation has been things that we could have done better with the DANDE mission, that it did meet minimum mission success, continued for further 2 months of operations after that point. Really was a very successful mission. And our major lesson learned to integrate the operators with the satellite and the ground engineers early in the design process to make sure that the final product works well for everyone. To think about those contingencies, or how our satellite respond, and then to keep track of the scope creep of the mission to make sure that all mission tasks remain attainable with the time and resources available, particularly for a student team. Next slide. I think the program sponsors that made this possible, particularly the Air Force Research Labs and the University on Satellite program. Without them, we never would have made it to a finished satellite, and then to the Space Test Program for actually providing a launch opportunity. Next slide. Also, many industry sponsors mentioned we've got a lot of mentoring help from them, test facilities. There are too many to go through the contributions of each, but without them, this mission would not be possible. Next.
Tanya, Franklin, that was a wonderful presentation. Maybe we have time for one question. I have one question. I assume you guys are students. Would you consider transferring to Utah State? That was a wonderful presentation.